So when we test for concavity, if the second derivative is greater than 0 for all the values of x in that interval, then it is going to be concave up. A minimum can occur when a graph is concave upwards. If it is less than 0 over that interval, it is going to be concave downwards. And a maximum can occur over that interval. So think about that. If I have a graph where it's concave upwards, then I could potentially have a minimum point here. If I have a graph where it's concave downwards, I could potentially have a maximum. I could potentially have a maximum here. If f of x is equal to 0 or f prime of x or f prime of a does not exist, there may also be a point of inflection. The second derivative can be used to analyze the graph of a function for intervals where the graph is concave up or concave down, and to determine points of inflection. So for example 3, determine where the graph of y is equal to x cubed minus 3x squared plus 4x minus 5 is concave upwards and concave downwards, and determine if there are any points of inflection. So to start with, if f of x is equal to x cubed minus 3x squared plus 4x minus 5, then f prime of x is going to equal 3x squared minus 6x plus 4, and f double prime of x is equal to 6x minus 6. I can also factor that down to 6 and x minus 1. I'm going to solve the significant numbers for when f double prime of x is equal to 0 or is undefined. There's not going to be any undefined ones in this case because it's just a polynomial. So if 0 is equal to 6 and x minus 1, then we know that x is equal to 1 is our significant number. Then I'm going to determine the intervals for concave up and concave down using my chart. So I'm going to set the intervals. And redo that line. And I know the intervals based on my significant number here are going to be going from negative infinity up to the significant number of 1, or from 1 up to positive infinity. I'm going to have the factor of 6x minus 6. What that means for my f double prime of x and what that means for my f of x. So if I pick a number less than 1, like 0, then this is going to be negative. If I pick a number greater than 1, like 2, then this is going to be positive, which means that my second derivative is going to be negative, and then positive. When my second derivative is negative, then it is concave downwards. When my second derivative is positive, that is concave upwards. And where it changed from concave down to concave up at the significant number, I'm going to have a point of inflection. So because I went from concave down to concave up at x is equal to 1, there is a point of inflection at x is equal to 1. I'm going to solve my point of inflection by subbing that significant number back into my original function. And we're going to get a point of inflection at 1 and negative 3. And then lastly, as we always do, I just want a statement. Therefore, the graph is concave up on 1 to infinity and concave down from negative infinity to 1 with a point of inflection at 1 and negative 3.